In today's world, there are dozens of different engines and dozens of different carburetors. At Briggs & Stratton, we know that your business depends on your ability to diagnose engine and carburetor problems quickly and on your ability to correct those problems on the first try. That holds true whether you're working on an older style carburetor or the state of the art. A solid understanding of carburetor theory is your key to those quick and efficient repairs. You see, troubleshooting through guesswork does not work. It's time-consuming, expensive, and frustrating. Successful troubleshooting means that you understand what is supposed to happen, you know how to test for whether it is happening, and you know how to interpret results. And yes, experience plays a big role too. It's our responsibility to provide the knowledge of carburetor theory. That's what this video is designed to do. The experience? Well, you'll need to supply that yourself. Let's begin with a basic review of how all carburetors work. We'll do that by building one from the ground up, just as we did in our previous carburetor theory video, PM5127V. Carburetors begin with a simple tube. One end of the tube has a flange, which lets us attach the tube to the engine. This tube directs air into the intake port. Next, we need a fuel supply, so we add a bowl of fuel below the tube. But how do we get the gasoline from the bowl into the air passing through the tube? We use a little pressure. You see, there's a principle, Bernoulli's principle, which basically says that if you increase velocity of a fluid, in our case air, in a confined area, you see a decrease in pressure. So, we need to decrease the air pressure in the tube by increasing the velocity at which the air is moving through it. We do that by creating a narrowing in the tube, known as a venturi. The air must increase its speed in order to maintain the same volume of air passing through the venturi. The result of this increased airspeed is an area of low pressure within the venturi. This pressure difference between atmospheric pressure and the lower pressure in the venturi can be used to push fuel. We know that if we put some gasoline between the high and low pressure areas, the higher pressure will push the gasoline toward the lower pressure, through the tube, and into the airstream. We just need a way to get sustained high pressure on the fuel in the bowl in order to maintain fuel delivery. So, we add a bowl vent. It allows air pressure to continually press down on the fuel in the bowl, which in turn pushes the fuel up the tube and into the venturi. At this point, we have a simple working carburation system, which would allow an engine to run at one speed. But in most cases, one speed's not enough. By adding a throttle plate to control the airflow, we can also control the engine's speed at any given load. A fully opened throttle plate allows maximum airflow, and that increases the difference in pressure between the surrounding air and the air moving through the venturi. As we close the throttle plate, the airflow and the air pressure difference between the atmosphere and the venturi decrease. As a result, the fuel flow and engine speed decrease. But we need better or more accurate control over the flow of fuel coming through the tube and into the airstream. What you see here is one solution, an adjustable needle, which is common on older style carburetors. In newer carburetors, you're likely to find a fixed jet system, and we'll look more closely at those a little later. Either solution will take care of most of our engine's needs. But what about when an engine needs to run at very slow speed? We could slow the engine by continuing to close the throttle plate, but eventually we'd reach a point where the air pressure difference is too small to continue to push fuel up the tube. When ability to run at slow speed is a concern, an idle system can solve the problem. Here's how it works. While closing the throttle plate lessens the air pressure difference between the venturi and the fuel bowl, it increases pressure differences in some other areas of the carburetor. One place where we can gain a significant pressure difference is between the engine side and the venturi side of the throttle plate. As the throttle plate begins to close, the air moving past it increases in velocity. and that results in decreased pressure at the edge of the throttle plate. We can use this pressure difference to move fuel at slower engine speeds. By creating a passage from the fuel in the bowl to the engine side of the throttle plate, we can use that area of decreased pressure to allow the higher outside atmospheric pressure to push fuel through the idle passage and into the airstream. Now, when the throttle plate is open, fuel is pushed up the high-speed tube. And as the throttle plate begins to close, fuel drops down the high-speed tube and is pushed up the idle fuel passage instead. Again, we want to be able to fine-tune the amount of fuel entering the idle circuit. So, we'll add an adjustment needle here, just as we saw earlier in the high-speed system. Now, we've completed our basic carburetor. If we attached it to an engine, it would do the job. However, we can still make a few improvements. For example, a choke system to make cold starting easier. Another modification, which will allow the engine to run more efficiently, is the addition of an air bleed to the main nozzle or emulsion tube. The air bleed allows a metered amount of air to enter the tube along with the fuel and starts to break up or vaporize the fuel before it even enters the venturi. Since it's the gasoline vapors which actually burn, this improves the engine's performance and also offers low pressure relief under no-load conditions. An air bleed can also be added to the idle system to provide similar benefits, as well as preventing extremely rich running at no-load idle speeds. A final modification involves improving the smooth acceleration of the engine from an idle RPM to a top no-load governed speed. You see, when we switch from the idle to the high-speed circuit, there's a momentary lull in transferring fuel from the bowl to the airstream. One solution is to add some transitional fuel passages to the idle circuit. Now, as the throttle plate opens and the engine accelerates, the low pressure area moves to the transitional holes. These passages add fuel to the airstream and maintain fuel supply to the engine. Now that we have a working carburetor capable of sustaining engine operation for as long as the fuel supply lasts, and a working knowledge of basic carburetor theory, is that enough? In today's world, the answer is no. The past few years have seen a number of enhancements in carburetor design, changes which you must understand in order to successfully troubleshoot and repair newer carburation systems. For example, since the mid-1980s, fixed jet carburetors have become more common in many engine applications. In some carburetors, the idle circuit has been removed. This was done both to provide consistent performance and to comply with new emission control standards to be implemented in the near future. This change affects only engines which are rarely run at idle, such as rotary lawnmower engines. Our customers have dictated some changes as well. Pilot jets and anti-afterfire solenoids are examples of components developed specifically to meet customer expectations. And finally, new standards for emissions have resulted in a change from adjustment screws to idle mixture adjustment limiter caps, and in some cases, the removal of all adjustments. Let's take a closer look at some of these changes and the theory behind them. In the carburetor we just finished building, you saw two areas where the air-fuel mixture could be adjusted: at the idle circuit and the high-speed circuit. Many technicians thought these adjustments were replaced by fixed jet systems to prevent tampering by consumers or technicians. That is just not the case. One important reason fixed jet systems were developed was to address a common problem: vapor lock. You see, gasoline actually prefers to be a vapor. When it is in a controlled environment, like a tank, fuel line, or fuel filter, the vapor can't readily escape, so it forms bubbles instead. All fuel systems contain small bubbles of gasoline vapor, and they are especially common in a carburetor's fuel line and circuits. There are three factors which influence the number and size of the bubbles formed: the volatility of the fuel, the temperature of the fuel, and the vibration in the system. Normally, these bubbles pass through the fuel lines and carburetor circuits without incident. If any of the three causes we just mentioned are present, however, the size and number of bubbles can increase. In recent years, it's become more common to use blended fuels, which combine gasoline with alcohol and ethers. The more alcohol or ethers in the blend, the hotter the engine runs. The higher temperature increases bubble production and increases the chance of vapor lock, which can affect engine performance and may stop the engine from running at all. Let's take a closer look at how those bubbles and vapor lock created problems in some adjustable jet carburetors. As the bubbles increased in number and size, occasionally one would lodge itself at the annulus of a jet or needle and seat. That bubble now takes up space, which would normally contain fuel, and in effect leans the mixture in the carburetor. When an engine runs under lean conditions, the temperature of the engine rises, and so does the temperature of the fuel. This, in turn, causes another increase in bubble production, and more bubbles lodge between the needle and the main jet. This creates even leaner conditions, which raises temperatures, which creates more bubbles, and on in a vicious circle. Now our carburetor has become little more than a bubble-building machine. As the bubbles become bigger, the number of bubbles begins to decrease. That's because the size of the bubble is controlled by its internal pressure. And when two bubbles with approximately the same internal pressure touch, they join together. Eventually, we can wind up with a few big bubbles. When the internal pressure in those bubbles becomes equal to or greater than the head pressure of the fuel, all fuel flow stops. And that is vapor lock. Now that we have a better understanding of vapor lock, let's see how a fixed jet system corrects it. In a fixed jet system, there's one relatively large hole for the fuel and the bubbles to pass through. In fact, the area of that single hole is equal to the total fuel flow area for an adjustable style carburetor when it is properly adjusted. Only an extremely large bubble could possibly block that hole and create vapor lock. Now, how does the fixed jet system actually work? An important component is the emulsion tube. This tube has a series of holes and a sealing area. It may also contain a jet or orifice. An important point to understand is that the jet limits the amount of fuel that is allowed to refill the emulsion tube when the engine is running. The fuel level in the emulsion tube varies based on engine load or throttle plate position. To understand how the emulsion tube works, let's look at 4 examples. When the engine is running with no load, the fuel level in the emulsion tube is the same as in the bowl. The fuel is being delivered through the transitional holes. So far, the engine doesn't need any more fuel than can easily flow through the jet near the base of the emulsion tube. Now, let's look at what happens when the engine begins to work under a light load, such as turning a mower deck. As the engine begins to work harder, the fuel level in the tube drops slightly below the fuel level in the bowl. The jet is a limiting device. Only a specific amount of fuel can flow through the orifice in a certain amount of time. When the engine uses more fuel than can be allowed through the jet, the fuel level in the emulsion tube drops. When the engine is running under a moderate load, the level in the tube drops even further. At this point, there's a significant difference between the level in the tube and the level in the bowl. Again, the limiting factor is the amount of fuel that can pass through that orifice in a certain amount of time, compared to the amount of fuel the engine is actually consuming. At this point, the high-speed air bleed feature comes into play. The air bleed acts a lot like a bowl vent. It allows atmospheric pressure to act on the fuel in the emulsion well. With sustained pressure and airflow into the emulsion tube, fuel and air are forced up the tube and into the venturi. As the fuel level decreases, it exposes holes in the emulsion tube to the air entering from the air bleed. This allows more pathways for the air to get into the tube and start mixing, which speeds up the vaporization process and helps the engine run more efficiently. Our 4th example is when the throttle plate is wide open and the engine is doing all the work it can. The engine needs the maximum amount of fuel that can be supplied through the jet. As a result, the fuel level drops until there's essentially no fuel level at all in the emulsion tube. At this point, the fuel flows directly through the jet into the emulsion tube and is delivered to the venturi. Now, let's take a look at another aspect of today's modern carburetors. In systems which still feature an idle circuit, you'll often find a pilot jet, a fixed jet for the fuel introduced into the idle circuit and into the transitional hole reservoir. The pilot jet restricts the fuel coming up from the bowl into the idle circuit as engine conditions change. At idle, the fuel delivery is not restricted very much. That's because a very small amount of fuel is needed to maintain idle speed. However, when the engine moves to top no-load speed or becomes lightly loaded, the pilot jet begins to affect the engine's performance. The size of the pilot jet's orifice provides just the right amount of fuel needed to maintain the proper speed when the engine is lightly loaded. As the fuel and air begin to mix in the pilot jet, the mixture may move into a cavity where transitional holes are drilled. This cavity or reservoir will be covered by a Welch plug. The holes shown here deliver the fuel when the engine is idling or under light load. Some carburetors provide a mixing area within the pilot jet itself. Different pilot jets are used in various carburetors, depending on the application. Now, let's look at one more relatively new component of modern carburetors. We've all heard the awful sound of afterfire that sometimes occurs a few seconds after an engine is turned off. Even though the ignition's off, most of the physical principles that make the engine work are still operating. As the engine slows, the governor responds by opening the throttle plate wide. Fuel flow continues even though the ignition has been shut off. The result can be afterfire. To prevent this from happening, anti-afterfire solenoids have been developed. They work almost like an electrically controlled plug. When the ignition switch is in the on, run, or start position, battery current is applied to the solenoid. This causes a spring-loaded plunger to retract into the solenoid's body. When the engine ignition is turned to the off position, the current to the solenoid is cut, and the plunger returns to its relaxed, extended position. This forces the plunger into the emulsion tube and prevents any more fuel flow to the engine. With the fuel flow cut off immediately, there's little chance of afterfire. Throughout this video, we've discussed the theory behind all carburetors and some of the features you'll find on today's modern carburetors. With this knowledge, you'll be prepared to deal with older carburation systems, newer carburetors in use today, and the carburetors of the future. This knowledge is your foundation for troubleshooting carburetor problems. Now, it's time for you to put that knowledge to work for your customers.